liking is this problem of working with a particle or antiparticle, right? I kept saying, why don't I work instead of working with a right-handed electron? Why don't I work with a left-handed positron? And I could see some sort of struggles, right? Now, maybe the point is there because there are actually two fields. It could be. But let's take an example just to emphasize that. If I take a complex scalar field, phi, which is complex, right? Then I write some Lagrangian, which is 1/2 d mu phi squared minus a potential, which actually is going to be a function of phi. Notice it doesn't depend whether I use phi or phi star. This is manifestly invariant, both the kinetic and the... But then I could add a fermion with the Yukawa coupling. Remember how we used to write psi L bar, phi, psi r? I'm sure you would have no problem if I had called this phi star. I could have written here phi star. After all, I don't know what the contour numbers is. I'm inventing them as I go along, okay? Even I give you two examples. So phi goes to C, there is also phi star. Is a complex number. And I could say, oh no, I'd rather work with phi prime, which is phi star. There will be no difference, you agree? The quantum number would be opposite if I had written. Okay, do we all agree on that? That there is nothing confusing that instead of phi I write phi star. There cannot be. So this is some simple example now. When we are in the standard model, then I have my doublet. Remember, in my doublet I gave it a hypercharge +1. I defined it again, and this was defined in the Yukawa interaction. Before I do the Yukawa interaction, it's irrelevant. We had absolute value of phi entering. Phi dagger phi, right? In the standard model, the potential is a function. Manifestly, I don't want to write it even phi dagger phi, so there is no distinction between phi and phi dagger. The distinction comes here when I write the Yukawa coupling, and I say that there is, say, Yukawa down, QL bar, phi dr, for example, right? And then the Yukawa up looks QL bar, phi tilde, UR. And there is also for that. What is phi tilde? Who wants to remind me? There is an antisymmetric tensor, and then it's a complex conjugate. I could have worked with phi tilde. Actually, I looked up just for fun to see. In his original paper, Weinberg, he has an opposite convention from me. Weinberg calls this phi. Okay, so let's call this phi boron, okay? That's how I introduce it. But phi Weinberg, and maybe I should have respected the father of his notation, but actually he wrote it for leptons. There is just one coupling, so it doesn't matter. Here we have 3. Phi appears twice, so I have less tilde to put. Anyway, phi Weinberg is phi Goran tilde. And we can as well work with phi Weinberg. Now, so you, when you see a complex number, you can work with a complex conjugate. That cannot be confusing. I hope it's not at this point. So you tell me, do you have any problem at this point? Or this is completely natural? It's just notation, right? We cannot be slaves of notation. Whatever conventions we have, we should also be flexible enough to be able to break them, to violate them. Okay? It's really just like saying that I call this left. And you get used so much, so if I start calling this right, you get upset. It's just a convention. I could call this my right arm, nothing would have changed. It's the same thing when I have left and right. I can choose what I call left or right, whatever I decide. So when I have a field and a complex conjugate, the name I choose. Okay, the difference is that the hypercharge of phi Goran is +1, and the hypercharge of phi Weinberg is -1. Let's write like this, the function. It's opposite field. So, in the same manner, let's forget two fields. Imagine that I have a field, a fermionic field psi L. Just like when I have a scalar field, I have phi and phi star. Same is true. And they have the same Lorentz properties. Okay, this is very important. Why do I want to emphasize that? There is no difference between phi and phi star except for the internal photon number. If one has charge 1, the other has charge -1, but they're both scalars. They're equal under Lorentz. And then you check yourself that there is IC, which becomes right-handed, which I can define like this. In the exactly analogous manner, the way I introduced phi star, I had to make sure that it has the same Lorentz property. And this, we said, is I gamma 2 psi L star. It's nothing but a complex conjugate. So I could have used this. Actually, if you look at the Weinberg paper that I'll be talking about in 79, I'll be coming to it constantly, he actually uses very often opposite convention again, somewhat systematically for me. And says, okay, when Goran works with psi L, I will work with psi CR, it's the same field. Okay, this is what I was referring to last time. I was saying only that. Of course, when there is a charge field at electron, there are actually two of them. There is EL and ER. And I can do that for each of them. But the point is here. You choose your field. And you say, I don't want to work with the left-handed neutrino, I work with the right-handed antineutrino. I don't want to work with the left-handed electron. Remember the relation was here, that EL bar, gamma nu L, which of course couples to maybe better minus, no? To conserve charge. This is, we found out, nu C R bar. There was a sign, I believe, right? Last time, who remembers? I think there was a sign difference. ECR. Well, it's not surprising, because what is here really is a left-handed electron. It's just disguised because I put a complex conjugate. And here I also put a complex conjugate. I decided to change the order, the only thing that happens there. Okay, this is what I've been referring to, and please, I hope this will somehow become more and more familiar. You will find it very useful for those of you that want to study supersymmetry, and especially if you're interested in grand unification. Remember, whatever the symmetry of the world, whatever the gauge group I have, when I put the fermions together in one representation, they must have all the same parallel. Lorentz group must commute and must be preserved. So when I take this particle number 1 into particle number 2 by whatever rotation in the group, okay, I don't want to break the Lorentz group. I cannot take, this is just a particle turning into the same species by Lorentz. So that's why it's convenient, I said, in the standard model. The bottom line was here. Okay, this is a little sort of, once again, a digression, a summary of this notation that I insisted. We decided to call this left when electron appeared. This is our definition of left with a neutrino. So don't get confused. I think this was Mehmet who was getting confused, but right-handed neutrino is there or not? No, there is no right-handed neutrino. There is right-handed antineutrino. That's always there. Every particle has an antiparticle. The ER is not an antiparticle or anything. It has nothing to do with the L. It's just another state. And then we said, I will work with ER. This is very cumbersome when I have to unify. So some people say, well, I want to unify. For example, if you look at the Georgia and Gletscher, 1974 SU5 paper, they will say we are forced now to choose the same plurality, and they will say, no, let me work with ECR. Just a complex project. That's the message. I hope this little summary will help you. And this is very important when understanding the Majorana. Understanding Majorana deeply is this capacity to go from state to anti-state, because sometimes you use actually one and sometimes the other notation without paying attention. Anyway. What we wanted to do the other day was to construct a Yukawa interaction that could give neutrino mass. What did we conclude? It was very easy. It had to be, well, why we decided to do the Yukawa way, hoping that the same mechanism worked, but not only because of that, because somehow we just couldn't satisfy the symmetry principles. This was not allowed, and we know that neutrino is massive. We made it invariant by writing this. This was dimension 5. So it's cut off by, this is called Weinberg dimension 5 curve. So I ask you to give it a thought and try to come up with the SU2 covariant, invariant Lagrangian, but SU2 covariant notation. So nobody did this? It's a little homework. These are the things that you either do immediately or don't do that. If you can never do that, if you can never, this will help you a lot. I'm not saying that I always do it, but I love when I do it. You just go for lunch and say, let's try where we are having lunch. That will make all the difference in the world. Because later on it's gone, and if you don't, anyway. You have, let's see if you want to try.
Yes, but I think I'm going to just say random.
Because there is no neutrino. I can't write like this, there is no left-handed neutrino. The only thing that exists is this.
Yes.
Right? I have no right to separate it yet. I'm at the level of the SU2 cross U1 in Lagrangian, there is a level of states. The same way that when I write the neutrino, I don't separate one of the components. Lorentz components, there are all four of them hidden here, or two, whatever.
No, we can use phi to select it.
We can use what?
Phi fields, which are doublets.
Yeah, sure. But we had to write the operator. There was an obvious candidate, we said. Well, let's just have this. These are our protagonists. We said this would work beautifully. LL transpose. I know how to make Lorentz invariant. I just put charge conjugation. I know how to put how to write an SU2 invariant. Oops. I just put I sigma 2. This is perfectly invariant under Lorentz and under SU2. It's not invariant under hypercharge, but it's okay that I respect it. I can write this. I have two doublets. Where phi is 0, phi 0. My unitary gauge, the physical Higgs field, not Weinberg's, Lorentz. Okay, Weinberg would be opposite. Weinberg would have, Weinberg would have phi 0 as an upper component. He took phi tilde, he took hypercharge minus 1. Okay. What was the problem with this?
That's 0.
That's 0. So by first attempt, let's say, doesn't work. Then I said I can, and I suggested, I gave you a hint, but you didn't use it. I could try to make a triplet here. Put Pauli matrices, okay? It gets a little messy, okay? Let me stick to the simplest way of taking two doublets and anti-symmetrizing, okay? I have two doublets, remember, one is LL and the other is phi. So who says that I have to do it in this order? Just do it in another order. So let's try this. Try LL I sigma 2 phi. This is an SU2 invariant. You agree? It's good that it's protected nicely. There is a computer inside. It's light enough and protected. I don't have to worry. I want us to be sure of this. This is the art of constructing, if you wish, effective theories of physics beyond the standard model. You notice it's also U1 invariant. These guys have opposite hypercharges. This has hypercharge -1, this has +1 by our conventions, remember. That's how we could write the Yukawa couple. But it's not Lorentz invariance, of course, it's nothing. So I go on, you agree? This cannot be the whole story. This is a spinner, okay? I need a scalar here. Okay, I'll just repeat it. I'll take phi transpose I sigma 2 L. This thing is also SU2 cross U1 invariant. Again, 1 minus 1 hypercharge. Because of I sigma 2, I'm taking two spinners, I'm getting an invariant, okay? So each of them is SU2 invariant separately. It's almost Lorentz invariant. I have a doublet and I have a doublet, but if I want to make it Lorentz invariant, I should put charge conjugation between these two doublets. Because there is actually a Lorentz index hidden here that I should have written explicitly. I cheated here. This is still a Lorentz spinner. It had an index implicitly there. So I have to anti-symmetrize again the way I did here. I have to anti-symmetrize twice. Please remember, there is SU2 which has nothing to do with Lorentz, it's an internal symmetry, a gauge symmetry of the standard model, and there is an SU2 which is hidden in the Lorentz rotations. Lorentz is very, very similar to SU2. Remember, it's almost like that, you know, with just a little sign. If the time was, well, it would be a strange life, right? But we could go back and forth in time.
Why the first one was 0 and this is not?
Can someone else answer? Or? This is the same state. This is symmetric. This is in the case of scalar, this vanishes. And in the case of spinners, it does not vanish. You see why? Because they anti-commute. It's another way of saying it. This is perfectly okay. We'll see that. Okay. It's just okay. It's hidden here. This is what you have been used to. Although there is anti-symmetrization, this works because this is also anti-symmetry. The anti-commutation of field, so this is okay.
You should then have in the first term like a transpose over the spinner indices, kind of. Because I'm not getting.
Depends what you mean by spinner. These are SU2 spinners. I know you mean the Lorentz spinner,
Yeah,
right?
the Lorentz spinner.
I put.
That's not for the SU2 in this, or?
Well, once I put it, it does everything.
Oh, it does everything.
When I write L transpose, I transpose it, obviously, both as a SU2 doublet, but also as, so in other words, okay, good question, just to clear it up, okay, you see, this is what I want you to ask me, please, there should be no confusion. So when I write L transpose, this is actually nu transpose E transpose. I transpose it both, as in SU2, what Nicolas is asking, and then inside I transpose it in the Lorentz. Meaning, this is my form of writing Weinberg operator. This is manifestly Lorentz and SU2L and U1 invariant. So I can do what Weinberg did is the analog of Fermi did for weak interactions. If neutrino has a mass and I don't want to introduce new light particles in the standard model, I believe that what I have seen, just same way that Fermi argued, I'm not going to introduce some whatever state, I'll just write the interaction that has to be the form at low energies.
We write phi Weinberg, as we said at the beginning, with the phi 0 above. We don't need the I sigma 2 in the middle, in between, right?
If you wrote
with the phi Weinberg we mentioned.
Suppose Nicolas is asking that I work with phi Weinberg, which is phi Goran tilde. Okay, then I would just write phi tilde here.
Oh, but okay. So the I sigma 2 makes it. I think we use the I sigma 2 too.
Well, Weinberg has a doublet. Remember, this is also a doublet. Right? It's how to emphasize it? Well, it's there. Once it's there, instead of phi Goran is phi Weinberg tilde. So if I work with phi Weinberg, I would put phi tilde. You agree? There would be I sigma 2 because it's also a doublet. This is also a doublet. It's not an anti-doublet. There are only two ways you can write invariants when you have two doublets. One is phi 1 dagger phi 2 when you have two doublets. From the SU2 point of view, with a hypercharge, of course, what will appear may be a tilde and so on. Here a tilde is needed to get the correct hypercharge, otherwise you won't get correct hypercharge. But there are only two types of invariants. Either you take phi 1 dagger phi 2, or you take phi 1 transpose. I sigma 2 phi 2. Whenever you have two doublets, phi 1 and phi 2. Here in particular, we could call this phi 1 if you wish, and this we call phi 2. Because there are actually two doublets. Only one is a complex conjugate of another. When there is a complex field, there are actually two fields. That's all I'm saying.
Why don't we just decodify?
Sorry?
Why don't we just decodify instead of using IC?
Why don't we do what?
Decodify using the first implant.
I could try that. So let's come here. I'm going to do this very pedagogically, and I will do it sort of in as pedestrian, manner as possible. So profit from there. There is one invariant which is phi dagger phi. There is no problem with that. Notice this carries no hypercharge, you agree? This is already invariant. So now I need an analog here, but this carries hypercharge. I can surely write that, but I don't know what to do with the L fields, how to write a Lorentz invariant. When I have this sort of Decker type invariant, then I have to write a Dirac type invariant. But then I need another LL bar. LL bar is not Lorentz invariant. And there is no way I can do it. The only thing I can write is this. And this carries hypercharge. If this did not carry hypercharge, then it would work. But it carries hypercharge. And the reason is, you see, the way the fermions got the mass in the standard model is because there were actually two fields, so they could help each other to adjust with the hypercharge. There was a left-handed electron and a right-handed electron. Here I have just one guy. And I can't do this other Dirac invariant. Okay, just like here, there are two SU2 invariants. And we can even give them a name of Dirac and Majorana type, just for fun, because they imitate what I can do with the fermions. With the fermions, I have two invariants, Psi L dagger Psi A. Let me call it Dirac. Or Psi L transpose C Psi L. There is no other way I can write the invariant. Of course, I could rewrite this one. By the way, you can say, well, Rana, you can say, well, this is just a matter of notation, maybe what Kevin is referring to. Let's go on. You're saying, well, why don't you do, you always tell us that you can work with, instead of CL, why don't you work with Psi CR? You can write this like this. This, for example, this is equal to this. Right? Why? Because this is C Psi L bar transpose bar Psi L. This is C gamma 0 Psi L star dagger gamma 0 Psi L. This is Psi L transpose gamma 0 C dagger gamma 0 Psi L. Gamma 0 goes through and you get precisely that. But you see, of course I can pretend, it's a question of notation, I can always, and I did that when I defined the Majorana spinners to have the usual Dirac way of writing a 4-component spinner. I can rewrite Majorana invariant in the Dirac form, but this is not a Dirac form because this breaks all the quantum numbers. Psi C has an opposite quantum number. Actually, we see it better here. When in dilemma, which one is, okay, you will decide. Sometimes you will use this, sometimes you have to get used to it. This is more transparent because it has immediate that you're breaking all the charges. Here you have to think a little bit, but not too much. Psi C has the opposite quantum number. So psi, when I take a bar, I'm back in a triangle. So therefore, that invariant will break hypercharge. I can't help it. The only invariant that I can make out of two lepton field necessarily breaks hypercharge.
Is it all because neutrino is neutral? Otherwise,
It's even worse if it.
I mean, I'm sorry, I cannot remember why we eliminate all the other possibilities, but what I'm trying to ask is, both for SU2 weak index and spinor index, we can choose Dirac or Majorana term, right? By putting a charge conjugation or other sigma term.
Let me make sure that I'm being clear here, because there may be some confusion still from the way you're asking the question. Why do I distinguish these two? This one breaks the quantum numbers in question. This one does not. Okay, when I want to associate this into one and the same particle, left-handed and right-handed electron carry the same charge, the same whatever, physical at the end of the day. Where this one breaks them, okay? I can pretend that this is thought of the Dirac form, but it's not, it breaks the corresponding symmetry.
So, first of all, why did we choose that one for thinner.
Which form?
Like, why did we choose the dipole number breaking form? We had a reason for that, right?
No, I mean, these are we didn't choose anything. I'm saying these are, no, well, the art of doing physics is that you and I try to listen to what nature tells us. So what nature tells us are in the language of gauge series, are the invariances of your underlying structure you start with based on the symmetries that you're exploring. So I'm writing whatever I can write. I'm not saying that I'm choosing this, I'm saying I have two options which are Lorentz invariant. That's a mathematical statement, it's not a physical statement yet. These are invariances. So when I build my theory, I should write, remember what I told, how I introduced the notion of renormalizable Lagrangian, what at the end we learned from it Hopf and the people that followed him. You have to write, if you want to have a renormalizable theory, the most general symmetric Lagrangian. So if the term is allowed by the symmetries, put it in. I'll try to explain a little better in a few weeks why there will be a problem if you don't do that, because you may get infinities that appear in higher orders and so on. So then I go back to my, for example, in the case of electron, let's think of the electron. I can write the following mass term. It's there, it's Lorentz invariant. Why didn't I write it? It breaks U1. I said the rule is I should write the most general Lagrangian, but however, invariant under the symmetries. Okay, that's a definition of the gauge symmetry. Okay, so therefore I couldn't write it, but I should start like that. So when you are building a new theory, don't you choose the terms. Oh, I'm choosing a Majorana. No, that's not your right. You write to me the most general interaction. Let's see you and I at the end what comes out. By the way, this is great physics. If I do like that and at the end I get an interesting physical phenomenon, I love it much more than me choosing it. Okay, what you love about Einstein's theory of gravity is that when you follow his principle, everything else follows. That's a great theory. And not you saying, oh, you tell me that the light is moving in the field of the sun. Aha, I'll put something so that it's described. But that's not great physics. That's trivial physics.
So what stopped us from writing a direct curve for neutrino? Maybe it's a really silly question, but...
Where? Which direct? There is no noir.
So SU2 stops it from us.
Well, it's yes, right? Because I have only the L, which is hidden in LL, so the only variant I can write is here. Okay, that's one way of saying it, yes.
Okay, that's why we eliminated that term, and in my terms we choose the Majorana, right?
Well, you see here what happened is that by saying that I want to construct the minimal theory, and I was forced into the minimal theory in order to make predictions. If I don't choose minimality, all hell breaks loose. I open Pandora's box. I can start sticking any field I like. So I said the minimality forced me not to have noir here. But it makes the theory kind of crippling. There is a fundamental field missing. Noir is missing. So somehow it is the structure of the standard model that is responsible for that. It's good that we learn the lesson, because this is what I want us to do. What is it that makes the standard model fail when it comes to neutrino? Well, it's left-right asymmetry. It's sort of crazy, this picture, that the left and the right words are so different.
One more next question. And then, if we write to put two phi's, why didn't we choose Dirac type phi invariant?
Oh, here, no, that's Kevin asked. I'm sorry. Okay. Kevin, that's Kevin's question, that's not your question. We have, questions should have merit, the answers, so that's always an important question. I can do that, this is invariant, however this is not invariant, therefore I can't make an SU2 cross 1 invariant. Oh, I was implicit here, I'm glad you asked. Really, I should have said, let me try this. Of course, this will not compensate for the hypercharge And even for the SU2, this carries both SU2 and hypercharge. This guy is not a singlet of SU2. It looks like. But sorry, no, hypercharge. What am I saying? This is without sigma. No, this is. Take it back. That's why Kevin's question was good. It's a singlet under SU2. So this is. So let's summarize here. Just to singlet of SU2L, but not of hypercharge. Or better to say, not of U1 hypercharge. Not. Kevin has another question. He's been trying while we are talking. So this is.
I still don't understand the third way of writing it using the alternate.
Okay.
I don't understand whether it's a sigma to get this time.
Where?
So the third way of writing it, we put sigma factor.
Okay. No, this was the first way of writing. Actually, there are different ways of writing. We'll come to you. This was the second way of writing. The first failed. Why did it fail? Once again, because there were two possible invariants that could help me. The first one didn't carry hypercharge. The second one here. Okay, this was Kevin invariant. Didn't work, didn't carry hypercharge. And there was Goran's invariant which failed. Would have carried hypercharge. It would have been perfect if it was not zero. Imagine a standard model. Imagine that you like to have two doublets in the standard model. Or that something forces you to have two doublets. Then this would be non-zero. Because they wouldn't commute. This wouldn't be symmetric, okay? So if the standard model has two doublets, we would write immediately a possible. But I define the minimal standard model, define the world minimality and explains everything. So,
how introduce this interaction now to give mass to the neutrino? Is it within the standard model? It's not beyond.
No, the particles are within. When I wrote the Fermi theory, when I wrote G Fermi, psi bar psi square, the interactions of that time, there were only electromagnetic interactions. This is not within the theory of electromagnetic interaction. What is hidden here, it's actually a new physics beyond. It looks like, you could have told me, well, but this is the theory. No, because we know today that this is G square over 8mw square. But what we actually know, there was not mw square, but there was a propagator which carried momentum, and only when the momentum is very small. In other words, what is happening here, there is some momentum flowing here from some new physics, okay? So what Weinberg says, yes, I wrote the minimal model some years ago. This is in 1979, okay? Weinberg writes this effective opera. There were sort of different groups of people that arrived to neutrino mass, to the idea of the Majorana neutrino mass in a different manner, okay? This is Weinberg. And he said, okay, I will do what Fermi did. So it cannot be in the standard model, but I will assume that there are no new particles unless they're very heavy. So if they're very heavy, they are hidden here. Really, this could be the mass of a heavy particle. The same way that Fermi coupling constant is not some strange coupling constant that carries dimension, but it's a mass of some particle. I'll come to that. This is an effective theory we are doing. This is Fermi-like. And what we are doing today is an effective theory.
Implicitly we are introducing new interactions. We can think of this as a new...
Well, we want to do, well, yeah, but we are saying that we don't care because now the neutrino mass is so small that I believe that that particle is very heavy. That's why the Fermi said, it doesn't help me to introduce the W boson. He knew that he would immediately get. Actually, Fermi maybe even comments on the paper, I should look at that. My vague memory that he does. The same way that the QED, you see, this is QED. With some charge hidden there. Okay, but when you go to the lower energies, you get to 1 over Q square. E square. This is the effective interaction. Forget a photon. What you see is two electrons scattering on each other, or two electron and the positron, and so on, right? Originally, this is what people saw, okay? Photon, seeing photon in some sense came later, okay? So when I integrate the, why do I get to 1 over q square? Because that's the moment, that's the propagator of the photon, okay? So this is the effective interaction. So when Fermi law, once again, G Fermi, he said immediately, I will get immediately if I write this GW, psi bar psi. Of course, there are different 1, 2, 3, 4, okay, let me be symbolic here. I can get that, and he knows that W will have to be very heavy, or the coupling constant very small. And he said, I believe that the coupling constant is not so small, I have a new heavy particle, so I won't worry about the original theory. I will characterize the physics. This is a good approach when you are far from the energies.
But those are effective terms or interactions. We try to write mass terms, right? Which depends on the...
Well, but when we try to do that in the standard model, we introduce new type of interactions, which are today a beautiful window into the origin of masses. This is the beauty of origin of mass. He's taking us into new physics, new interactions.
So I would naively say that when I expand phi, I find vacuum expectation of Higgs.
Yes. Well,
over the Weinberg scale.
Well, right. We will now start talking. We will now see whether there is anything really interesting in Weinberg's operator. I would argue that it's not useful at all. Unlike Fermi, effective interaction with similar different processes, and therefore you could use it. There's a bookkeeping. Here we will see that nothing exciting happens. Okay, before I do that, a little more with group theory, because it seems that Kevin, you said you have yet another way of writing this. Did you say?
In the last lecture we introduced
the one that I mentioned.
Yes.
Right. I could also write, I said, L transpose C I sigma 2 sigma. I always have to put I sigma 2 when I have transpose. But if I put this sigma, this now starts to behave like some kind of vector under SU2 or SU3. Like here, phi transpose I sigma 2 sigma phi. There is yet another number 4, but please don't tell me now that you won't look at it, okay? I will be disappointed by Friday. Write to me one more. There is yet one more, okay? I don't want to write.
Why there is sigma 2 there?
Huh?
Why there is sigma 2 there?
Where? Oh, without I sigma 2 it won't transform correct. There are two ways of writing triplets in SU2. You either write phi dagger sigma phi. This is a triplet. This is a vector. Or phi transpose I sigma 2 sigma phi. This is also a vector. Call it V prime. Please show that. This is easy to see. This is actually seen that it behaves like a vector. I showed you that in some exercise. I remember. Then show that without I sigma 2 this wouldn't behave as a vector. You know how vector transform. We know that, right? We did. Okay. Let me not say more.
So it's like adjoint, right?
This is like the adjoint, precisely. But when there is a transpose here, the only way to get a correct transformation property is to use sigma 2. Just the same way in a Lorentz group. When there are two spinors, you see, because actually I have two spinors and not an anti-spinor. These are sort of statements to be proven. Okay, these are. Look, there are things that will be in the take-home exam. Some of the things that I say prove. If you do that, it will help you a lot in the take-home exam. Some of the things I will put in the take-home. Some of the things that you see, oh, but I'm not so familiar with group theory. If this is not clear to you, you better check it. And the reason here for psi sigma 2 is the same when I make an invariant. It's the same reason. There is yet one here, but remember how I did it. I just permuted fields, so think about permuted fields. Okay? I won't, this was just a side comment. I won't write it. That will be somewhere one day. I think probably I'll put it on the final. Let's see what we get now. Let's see whether we'll manage to get something interesting that will make Mehmet happy, because he worried that we'll just get a mass term, and he's basically right. Almost. But practically you're right, because phi is that thing there. So what will I get here? What is this? I will just get UL transpose phi 0, you agree? C, again phi 0 nu L. So this is, let me rearrange it, nu L transpose C nu L. Obviously C is acting here and here. These are, there is an alpha index, there is a beta index. This is what really happens, right? Which I didn't write here. There was an alpha index here. There was a beta index here. Okay, so what is this? What will I get? I will get V squared plus 2HV plus H squared. Although there are other ways of writing this Weinberg dimension 5 interactions, you will see that they reduce to one and the same. There are three different ways. One is, there are actually four, but one is 0. They all reduce to one and the same form that you should convince yourself. Let's erase this failed. And what do I learn from here? That I have a neutrino mass which is V squared over lambda nu. So Weinberg would tell you, if you're asking why is neutrino light, I know why neutrino is light, because lambda is large. Is that a good answer?
Yes, but then neutrino mass shows us a scale that we can...
Right, but I mean, is that an answer? Well, it's a trivial answer, because then the second question I would ask him, okay, is why is this large? Actually, it was very interesting. I was at the PASCOS conference last year, and there was at the same time the 50 years of the standard model, so they overlap. And Weinberg was giving a talk, and we entered into a heated discussion. But the organizer, he was sort of leaving, and the organizer even interrupted. It was very funny. They felt they should. Weinberg is not a young man anymore, but he knows how to protect himself. He's a great physicist. Okay, I was insisting. Weinberg was saying there is no reason to study the origin of neutrino mass, because I'm sure that this is very large. So you will waste your time if you Mehmet and you guys, will waste your time. Now notice very interesting thing. There was an effective theory of Fermi. Now Weinberg made a living by trying to understand the origin of Fermi. Now he's giving you a message, don't do that, because you know, this is large. Imagine him being a young man and someone telling him, no, look, Stephen, don't waste your life on trying to understand G Fermi. That's some new scale, okay? That's not too interesting, because I don't know what it is. It's psychological, because if you don't worry about it, you should keep citing Weinberg. Okay, I, on the contrary, will insist here that the task actually is to understand the origin of neutrino mass, and I'm deeply disagreeing with him and whoever says that nonsense, because this tells you nothing. As you said nicely, you may not be aware, at the end you are telling me, oh, neutrino has a mass, and you will see nothing else. That's very tragic. It could be like that. It could be that we are, unfortunately, living a bad era. In the next 20, 25 years, that you guys will be 30, 40 years witnessing development of physics, would never learn anything else except that neutrino has a mass. In English, you say, put your money where your mouth is, and therefore I tell you, I'm willing to bet that we will actually see the origin of neutrino mass. And I want to show you that it could even do with the colliders like LHC, okay? Because you see, the next question then you would have if someone tells you, don't ever get fooled. If someone tells you, I know why neutrino is large because lambda is large, then you should ask him, why is lambda large? That's not an answer. Okay? That's just the thing that is emerging from Weinberg's way of writing, which is very important. Because notice here that I could have written some coefficient, how should we call it? Shall we call it G Weinberg, but it looks like weak coupling. Let's call it Yukawa. I could have written a Yukawa as we did for the dimension 4 interaction. So really neutrino mass there is actually Yukawa. Let's call it Yukawa Weinberg. Okay, there are two possibilities. One is that this is very large. Astronomically large, you never see it. The other is that this is maybe small. So this is not so large. And you and I don't know a priori. The point is, however, and this is crucial, one fundamental point emerges, that neutrino is Majorana. There is a message which is physical. There is a good chance we should see neutrinos double beta decay because it's not a Dirac particle. If Weinberg is right and the new scale is large, then there is nothing but a Majorana mass term. Okay, for sure. Another thing that we want to ask you, how strongly is the Higgs coupled to my neutrino? Because that's how I'm looking for Higgs. I first find the mass for the electron, and then I see how it couples to the electron, right? That's what we did. And it's hidden here, so that's the second message I get. That the effective, let's call it Yukawa neutrino. What is Yukawa neutrino? It's here. There is a factor of 2. Let me not write a factor of 2. I'm interested in the scale. It's V over lambda nu times Yukawa W. You agree? This is my effective interaction of the Higgs. Agree? I read where the Higgs couples to this guy. It's proportional to V. And the original coefficient was Yukawa W over lambda nu. What is this? How should I write it? I should write it in a better manner because I could write this as Yukawa W V squared over lambda nu 1 over V. What is this? This is M nu over V. If you wish, we could put here my Majorana index. For a while, let's keep it to remind us that neutrino is Majorana. There is still a beautiful physics on neutrino is double beta decay. And you know I can write this as G over 2 M neutrino, which is of Majorana type over MW. So you see what would happen if Weinberg were right. And I hope very much that he's wrong. And I'm willing to bet all the money with him or any of you guys. To you guys, I would give different thoughts. Okay. This is ridiculously small. We will never see this. In a sense, okay, I allow for the possibility that the Weinberg is right, that this scale, okay, is, I don't know, 10 to the 15 GeV or something, so no machine will ever probe the new physics that Nicolas was asking before, okay, or maybe some of you guys. But however, notice that this is of the order, neutrino mass we know is less than 1 electron volt. We know that for sure. So this is less than 1 electron volt, and this is 100 GeV, that's 10 to the 11 electron volt. So this is less than 10 to the minus. So the branching ratio for the Higgs to the K into neutrino is, I don't know, 10 to the minus 20 or something. You have to square the Yukawa coupling. And you know it's an invisible decay. Higgs decay into neutrino is an invisible decay. Like a Z boson, you know, why you and I say the Z boson, there are no other light neutrinos? Because we've seen all that visible and invisible, we measured the decay widths of the neutrino. So the bottom line of this approach, the summary of dimension 5 Weinberg. I, neutrino is my Rana, so I expect to see 0 no 2 beta. Second, whereas it is true that neutrino mass is small if the scale is large, this itself tells me nothing. I tell you why it tells me nothing, because I don't know what the value of this coupling is. If I knew that this coupling was 1, then at least I would say that I know what the scale is. But I have no idea what this coupling is. And Weinberg wants to argue that this coupling should be order 1 for some reason. The scale is. Let's see what happens for 1. Okay, just to get an idea. If this Weinberg Yukawa is 1, what will I get? That lambda nu is V square. What is V square? V is about 100 GeV. That's W mass. So that's 10 to the 4 GeV square, divided by neutrino mass, which is 10 to the minus 9 GeV. So this is about 10 to the 13 GeV. Okay, Weinberg would be right. If you and I knew that this coupling was order 1, then it would be crazy to spend our lives trying to understand the origin and the nature of neutrino mass, because the scale is 10 to the 13 GeV, and LHC is this 10 to the 4 GeV. I've been waiting 30 years to go from 200 GeV, in other words, by an order of magnitude to well more, maybe 2 orders of magnitude, wait basic all your life in physics. But for example, if this was, I don't know, 10 to minus 6 or something, the way for electron I have a tiny coupling, what would I get then? Then the scale would be 6 order of magnitude smaller. I don't know what it is, guys. So this tells me nothing. Except that I should expect neutrinos of a beta decay. Weinberg tells me nothing. This is what I want to insist. This is not, I get no new physics. Why? Because Yukawa neutrino, the effective neutrino Yukawa coupling we saw is G over 2 mu over mw. Less than 10 to the minus 11. You and I want more than this.
Can we observe that?
Well, maybe you don't want more than this, but I'm telling you, we should want more than this. Why should you and I want more than this? I mean, doing physics is gold digging, if you really want to discover something. If you don't want, if you just want to play with equations, that's also a beautiful thing. So what should we attack? When we have to study where to go beyond, we should attack where the theory fails. This is the only failure of the standard model, neutrino mass. So I would like to do now the next step, what was the question that Nicolas was asking, well, how do I get this effective operator? Because it was good to know then when when there was G Fermi, how would I get G Fermi? People thought about it a lot. And then Glashow and these guys found you actually a beautiful, complete theory to give it. We should try to do an analogous thing. Just to give you an idea what it means to probe something. I feel obliged to say a few words more. And the reason is that I don't know how to study this. There is nothing else I can study. The guy who is telling you this is telling you don't study neutrino mass, study something else. Right? He's telling you, okay, neutrino is massive, but there is no new physics associated with it. You will see nothing. Nothing in the colliders. You will never see Higgs decaying, because now gamma, from here, gamma Higgs decaying into nu bar will be proportional to this terribly small Yukawa nu square. And therefore, this is zero for all practical purposes, right? We'll never see that. In other words, you and I will never know that neutrino got the mass for the Higgs mechanism, but our task is to prove that particle masses have their origin in the Higgs. Okay, so we should try to do that for neutrino. Okay? And I want to tell you, I devoted a good many years in recent years, and I feel I managed. Good deal of work with Vladimir Tejo, who was our diploma student, is to come up with the analogous theory. In other words, to do what Weinberg did for the leptons and Jim, to do something like that with neutrinos. I just outline where we will go. I won't. That's a physics beyond the standard model. But the first task is here that you and I ask how to get this operator. Because if I don't know how to get it, it's a force. I understood nothing. Okay. Also because this is probably not the approach that you and I would have followed. I, for example, didn't. I wouldn't have thought in this language. This was a really beautiful work of Weinberg, which he classified all the new physics, which led to baryon number violation, lepton number violation. Beautiful paper where this is hidden. I'll be referring to it. In the case of baryon number violation, he came up with a number of beautiful predictions, which here lacking. The reason here there is just one operator. And that was a great surprise that he managed to get so much. I, for one, would have worked on a well-defined theory. Okay. So, how to get the dimension 5 operator? Or better, maybe let's erase this. How would you and I think about neutrino mass? After all, maybe we should get back to what was bugging Mehmet or maybe someone else, but I remember saying, well, what is missing there is this, I'd like to be able to give this Dirac, while also you were asking me someone, could neutrino be Dirac? It could be. But what does it mean? This is sort of going a posteriori to someone telling you that neutrino has a mass. Forget this sophisticated way of Weinberg. Forget that there is any theory of nature that gives neutrino mass. You say, aha, you told me neutrino has a mass. Well, I'm going to put a right-handed neutrino. The reason that the electron had a mass, and I can see Mehmet is happy, for one. Remember that this particle actually is not a particle, it's a strange guy. It's a ghost. At this point it's a ghost because this guy has hypercharge 0 and it's an SU2 singlet. So the fact that I say that I'm including is just empty words. I didn't include it yet. Okay, you agree. At this point, this guy doesn't exist. It's propagating out there. But let's now couple it. So you are telling me, okay, when you did your Yukawa interaction, you wrote Yukawa electron. Well, let's be explicit. Nu E L bar phi U R. What you are? E R. Well, why don't we write a similar coupling for neutrino? So call it Yukawa nu E bar L I can't write phi, the hypercharges are different, but I have phi tilde. And that's perfectly okay. This has a hypercharge -1, but this has a hypercharge +1 because of the bar. This is invariant. It's always, for the quarks we had the same. When Higgs is coupled to down, Higgs tilde is coupled to up. This is up. There is a Hermitian quadrant. What would I conclude? The same conclusion that I get here. Phi is 0v plus h. Therefore, I get Yukawa E bar E, and I get the same thing, Yukawa nu bar nu, v plus h. Just like for the upper quarks. Now I got the master. So what I am predicting, that m nu is Yukawa nu times v, well, like for the other species, or better to say Yukawa nu is g over 2, m nu over m double. Notice, let's put the Dirac thing, because now this is a Dirac particle. Now I'm saying, no, forget neutrinos double beta decay, I just wrote the Dirac master, all the symmetries are respected in this particular case. And neutrino got a mass, it's true. Someone tells me neutrino has a mass, there is a guy, Alexei Smirnov, sitting here, as many other people, interpreting oscillations and saying, well, this means the guy has a mass. Okay, you do that. Okay, I tell him, I can do that, no problem. What I'm predicting again, that nothing is to be seen. Another tragic scenario. Possibility. I would hate to live in a world like that, but who wanted this possibility if this can be Dirac? I think, but who? No. I don't want this. There is more to it, however. This to me would be heartbreaking. There is a proviso here. What I wrote is actually not complete. It's not correct. I want you to remember Weinberg as a message. Remember that what we've learned from Weinberg, please, that the mass would always be 1 over some new scale. Be the thing that there are no new light particles, and the neutrino would be Majorana. This was, however, to be appreciated. But when this recent weeks I've been stressing that if you want to write the analog, the normalizable standard model, you should write all the invariant gauge interactions. And I didn't do it here. What is it that I forgot? There is something missing here. No, not gauge. No, because new arc has no gauge interactions. That I didn't even want to write it, but the guy, he's a phantom particle, doesn't exist. Why do I call it right-handed neutrino, by the way? It's not because I put it here, because I put it here. This is a definition of right-handed neutrino. Now it's coupled to the left-handed neutrino through the master. That's a definition of right-handed neutrino, but it's defined here. This is the definition of. This is why we call this guy often right-handed neutrino. By the way, there is a right-handed neutrino, there is also a left-handed anti-neutrino, that guy. okay? Don't get hung up on so much that it's right-handed. Why the name neutrino? It's because of here. If I don't couple it, this guy is not neutrino, it's nothing. But it's a gauge singlet. So what is it that is invariant that I would have written and I forgot? And people forgot this for a long time when they were thinking. But we've been doing this for the last 2 hours, 3 hours. There are two types of invariants I can write, I keep saying, Dirac and Majorana. I wrote the Dirac invariant, but I forgot the possibility of Majorana invariant. I should write it down and then check whether it's also gauge invariant. What about this?
Because it's neutral, we can write this, right?
Yes. I should write it according to the rules of the game that I kept stressing. Write down all the invariant interactions. Remember that there was actually Majorana, there should be m over 2 Majorana mass. We've learned that from the first model. That should be there. So see, from now I get, from this interaction here, what I get here, you know, because of that, what we do here, I will use the privilege of the bag, but this is not anymore Yukawa neutrino. The thing is going to get more complicated. This is what conventionally is called Yukawa Dirac. To emphasize, well, it was Yukawa neutrino, only I wrote an incomplete theory, okay? This was not correct. We should call this Yukawa Dirac. There are actually two mass terms here. One is Yukawa Dirac times V, nu L bar nu R, plus nu R bar nu L, plus M over 2, nu R transpose C nu R. Plus Hermitian conjugate. Let me write it. I have a complicated mass matrix to deal with. And a bit of a struggle of notation. I have a Dirac notation and Majorana notation. It's a little thing that is sort of hard. Here there is nu R bar. It's sort of a little. So I'll show you two different ways of arriving at this. But what the important message of this is, you and I want to introduce Arahan in neutrinos. We are going to open a Pandora box. It's not as simple, it's not as trivial, it becomes interesting. So I will rewrite this a little bit. Remember how I could write this? I could introduce, let me introduce, if you don't mind, this field. Now, why am I doing that? First, my neutrino, the one I would like to work with, is left-handed. So let me try to have another left-handed field so that I have a picture between these two guys which is symmetric. Also, now here is the argument a la Weinberg. Weinberg said, when I write my operator, I expect that scale to be large, because the operator is invariant under SU2 cross U1. It came from new physics. That physics is going to be beyond the standard model. That I agree with him. I don't know whether the scale, however, is 10 to the 13 GeV or 10 to the 5 GeV. That will surely be big compared to the standard model. The same argument here that we will now follow is that this mass term has nothing to do with the standard model. There is no Higgs mechanism here. There is no vacuum expectation value. This is the mass scale which is there already before I break SU2 cross U1. So the approach that has been followed was this a lot. In reality, all I need that this is much bigger than M Dirac. This I will call from now on M Dirac. Why do I call it M Dirac? This is the neutrino mass. If the right-handed neutrino was not Majorana, and it is Majorana by natural symmetries of the theory. Okay, it's allowed to be Majorana. So I'm suspecting that I will have a heavy particle. You see, you got a large mass. Go to the limit when V is 0. What do you get? A heavy particle and a massless neutrino. So I want to have another name. It's actually not a neutrino, it's some heavy neutral lepton. N stands for neutral, and I'm imagining it to be a heavy particle. Okay. Now, then I can write the following: mu R bar transpose mu L. Let me see if you tell me what is this in terms of N. Let me see how quick this is penetrating, this going from one notation. Yes. I can see. No. Well, mu R is N. So just think like that. If there is no R, it's going to be N, but it always has to be transposed, otherwise you won't get an invariant. You cannot take two spinors, you must take a transpose. And the only thing that can come here is charge. It's trivial. Nu R bar has this hidden. Right? N transpose. And L transpose is what? Nu R bar C transpose. Correct?
Minus.
No, it's okay. No, it's not minus C. I think CTC is 1. I'm pretty sure. CT is minus C. C square is minus 1. I think even the correct, there is no minus sign.
CT is minus C, then. Okay.
No, CTC is 1. I'm pretty sure. Anyway, there will be just a sign. So in other words, my Yukawa interaction becomes M Dirac NL transpose C nu L plus M over 2. But let me write this. Let me write this in a little stupid manner. I'm going to write this as M Dirac over 2 NL transpose C nu L plus nu L transpose C NL. I wrote M Dirac as a half plus half. Why? Notice that this is equal to this. They anti-commute, but C transpose is minus C. Plus M over 2. This term here is NL transpose C NL plus Hermitian conjugate. Well, there is a Hermitian conjugate anyway. This also has a Hermitian conjugate. Do you see this? The thing that I'm inviting you to see is this. What else would it be? We can just multiply by kappa 0, right? The way to do it would be to this I could write as nu R dagger gamma 0 C dagger. Do I need gamma 0? I guess. Let me try this. This is noir bar, gamma 0, C dagger, gamma 0, noir star. Noir bar is my NL transpose. C, gamma 0, C dagger, gamma 0, and noir star must be it's good to see what this is. What is this? This is C gamma 0 noir star. So noir star is gamma 0 C dagger, I guess, and this mess here is just C. There are 4 gamma zeros, they give you 1. 3 C's give you 1 C, because C squared is minus 1. Please check. Bottom line. Bottom line of writing things correctly, that I actually got a neutrino mass matrix between NL and UL, which has this form, MD, MD, and this large M. This M is often called MN, or MR, or M noir, or just N. Let's write here, N for the time being, as I did, okay. There is a factor of half, but remember it has to do with the kinetic energy, and then we do the 4 component, okay. The factor of half is misleading. There is no factor of half, because we will introduce Majorana states. This is a mass matrix. And this mass matrix is a little complicated, but we said that we are interested in the limit when M is much bigger than M0. So what are the eigenvalues? How quickly can you tell me when M is very large?
It's the last exercise of Senjanovic's class.
Yes, we are coming back. You're doing a full circle in time. Yes.
0 MD can, but MD is almost 0.
Sure, one mass term is. So in other words, there is, let's call it M large, is basically M. And then there is M small, which is, how quickly can you see it without doing the algebra quadratic equation?
Order of MD, but how much?
No, it's very important. Order and MD would have been if it was a Dirac particle. No, this is much nicer. Well, how to know it? What is the determinant of this? And the determinant is a product of 2 eigenvalues. So what is the other eigenvalue? There is a minus sign. Let me put it there. You may say, why are you worrying about the sign of the thing? Okay. Normally we don't worry about the signs. Remember we said of the mass matrix. In Majorana case, there may be something hidden here. Okay. Notice, however, they are both Majorana states. There are 2. Actually, there is no neutrino right. The right-handed neutrino becomes a heavy neutral lepton. I gave it a name N, which is very heavy if M is large. And then there is a light guy, which is predominantly our neutrino. Okay, so this would be what we call M neutrino. And of course, it's on Majorana nature. These are manifestly Majorana masses. And the physical states really. But I don't want to change the notation. There will be like this. Nu physical. My neutrino is nu plus theta n. And n physical is n minus theta nu. And theta, notice, what is the mixing between those states? It's the ratio of the off-diagonal and diagonal elements. Theta is md over m. There is a small mixing, in other words. Right? The eigenstates of this matrix obviously is not neutrino, but a mixture. This is what you did with spin. So you see what we are learning. When M Dirac goes to 0, neutrino is massless as it should be. Because I don't have a right-handed neutrino. There is no right-handed neutrino. There is nothing when M Dirac is 0. This M is some phantom particle, okay? So the way it works, this guy, you know, this is called the seesaw mechanism, okay? There are a bunch of us that came to this from different points of view around the same time as Weinberg was writing his operator. And one group was Gell-Mann and Tal. And Gell-Mann is very good with names. So he called it seesaw. I would have never thought of seesaw. This is why it's called the seesaw mechanism. Maybe Smirnov talked about it. So this is N, and this is Nu, and somehow, you know, the seesaw is N is very heavy, so it's just like the. Two things we are learning. When, notice that what I'm doing is I'm reproducing the Weinberg's operator. Weinberg says that neutrino mass must be of the order of some new scale. But notice an interesting thing. This is equal to minus Yukawa d squared over n times v squared. So notice that what I call the Yukawa-Weinberg over lambda neutrino is actually Yukawa d squared up to a sign, and I didn't worry about the sign over m. And this is the explanation of where Weinberg would be badly wrong. And this is the way we thought about it, Mohapatra and myself, for example. We argued, look, M Dirac, neutrino and electron live together. It is natural that M Dirac is similar to mass of the. What would be so strange if the neutrino mass was similar to the electron mass? That would be a natural thing, not some big mass. Okay, but the natural thing is basically you would argue Nu and electron is one and the same state. So now what happens if I assume that? Suppose I take that M Dirac is of order ME, just to see what I get. To give you an idea, this would give me Yukawa Dirac on the order of 10 to the minus 5, 10 to the minus 6. The scale wouldn't be large at all. I will get for 10 to the minus 5, I will get 10 to the minus 10 over m, 10 to the minus 5 over m, 10 to the minus 5, and this was 10 to the minus 13 GeV. We found out. Remember the Weinberg scale that he says. So Weinberg says, you guys, don't look at it because I know that the scale is very large. I say, no, I don't know. I can be dead wrong, but so can Kim be. I could live in the world in which Yukawa Dirac is similar to the Yukawa d electron. In that case, what I will get that M would be a TV. What's the difference? I could see this guy in principle. So I'm going to pursue that for the lecture. We have to summarize all this, okay? But before pursuing it, we'll try to summarize the thing that I want to emphasize here. I claim Weinberg taught me that neutrino should be Majorana, okay? But he also told me there is nothing new to see. So just go and work on strings or whatever, okay? Or do astroparticle physics, okay? But don't do this, okay? Now, a practitioner of the seesaw, is this any better than Weinberg? Let's make a poll. What do you think? Is this better than Weinberg? Is this equivalent? Is this worse? Who thinks this is better? Help me. 1, 2. Here we have 2 hands raised. Niloufar raised it very shyly, right? Half there, half Mahmoud is also shyly raising it, okay? I see Fatma is completely unimpressed. Here we have 4. It's about 4-4, okay? We are even, okay? Now, my name is associated with the seesaw mechanism. And if this was the seesaw mechanism, the way the people imagine it, I would actually say this is worse than Weinberg. Because it is true that I could maybe see a right-handed neutrino because it could weigh TeV. So instead of having this sad picture Weinberg, that makes you cry. But however, how would I produce it? How would I produce this bloody guy? Well, remember, it mixes a little bit with neutrino. So in other words, in the standard model I have G over square root of 2, W mu. Then I have minus, let's say, EL bar, gamma mu, nu L. This nu L actually is the physical nu L. I don't want to change the name. But then obviously there will be plus theta, EL bar, gamma mu NL. You agree? Because of the off-diagonal master, as we always had when the states mix, there is also mixing in the interaction. Therefore, I could produce, but I could produce it through theta. But what is theta? Actually, I would produce it through theta squared, you agree? Because the rate would go through theta squared. What is theta squared? It's m Dirac squared over m squared. What is this? It's m nu over m. So if this guy is TV, which I would like to see, what is this? 1 electron volt, this is 10 to the 3, this is 10 to the minus 12. I'm not going to produce a heavy particle with a coupling with the probability of 10 to the minus 12. The particles we produce at the LHC are particles who have couplings of order 1. We use gluon fusion, we use coupling to the gauge bosons, etc. All the couplings in the standard model are order 1. That's why we can produce those guys. Therefore, I could produce N if the couplings are very large, if M Dirac is very large. But if M Dirac is very large, then M is very large also. This is always small. There is no way you can boost it. The heavier it is, of course, the harder to get it to. But there is also energy that will cost you. It's not only how big the couplings will be. So, I would say the following. If you cannot imagine at all of producing a W boson, because there is no way that you could reach those energies or those strengths of the interaction, then Fermi language is better. Because it can describe all the physics that you have and tell you what is going on. It doesn't give you a false illusion of doing something which cannot be done. So, to me, I would say Weinberg seesaw is 1-0 at the moment. But we'll stop here, okay, it's the halftime. I would say if you and I want to understand, okay, this is a strong message. The origin of neutrino mass, we should do better in the season. This, similar to Weinberg, who says, oh, I know why neutrino is heavy. Like, because the scale is large, now I tell you, oh, I know why neutrino is light. There is a phantom particle that you cannot see, and it's very heavy, and it decouples. But it decouples in such a way that neutrino is light. You'll say, well, forget it, that's not a physicist explanation. And please don't accept these things as you go along, because it has become a common aspect of our field. That the so-called explanation imagines states that are decoupled, that reproduce the same thing that you have. Then it's better to say that neutrino has a mass, period. What maybe you can like, that the seesaw, just like Weinberg, tells you that it's Majorana, the nature. So we should see neutrino double beta decay. Well, let me summarize it maybe in another way. I have to finish now, 15 to 1. it's not so much to me to explain why neutrino is light. It is relating neutrino mass to some new phenomenon. I'm happy, I feel that Einstein does something deeper than Newton if he tells me that his way of understanding whatever it is leads to new physical phenomena. That, to me, is essential. Good physics should not be about understanding why numbers are what they are, but rather relating the things you are studying to a set of new physical predictions, okay, which are manifestly missing here. We are saying here that yes, there is a right-handed neutrino, and it has beautiful, interesting physics that will be, it decays. Once you're producing it, decays into the W and the electron, and you can see very interesting features of its decays that I'll talk about. But I cannot produce it. Okay. Just any last question?
This Higgs particle has existed since over that.
Sorry?
This N particle.
Yes.
Has existence always in the universe, and it's not coupled to anything.
Well, it is coupled a little bit. No, it is, no, let's don't say anything. It is coupled a bit to W boson. So actually, now you're touching into a nice question. It could play, okay, there is something where this does better than Weinberg, but it has nothing to do with this. Remember I talked about possibilities that you and I explained genesis. Genesis to particle physics is explaining two things. Why you and I are made out of matter. Why does it matter? It should be obvious. And then to also explain why that matter in the universe is so feebly distributed. There is almost nothing in the universe, right? Remember, please, this magical number, one of the most interesting numbers of cosmology, that the numbers of baryon over the number of photons, especially those of you interested in astroparticle physics, this is one of the most beautiful examples of astroparticle physics, is 10 to the minus 10. So the physics, the particle physics, the physics beyond the standard model, would be great if it were able to explain this number, arrive at this number. And yes, the existence of right-handed neutrino, because it was supposed to be there in the universe, and it's a little coupled to the W, and it's a little coupled to the Higgs we've seen through the Dirac mass term, actually is the most natural and the most elegant and the simplest candidate for what is called the leptogenesis in this case. You produce the excess of lepton numbers, but maybe you're tired, maybe I shouldn't. I would need 2-3 minutes to go on, or we can leave it for Friday. Leave it for Friday, but let's leave it for Friday. I come back to this issue. And I will actually come back to this issue when I finish the course. I will finish on this note, okay? I'll just mention it a little bit on Friday. This is a fundamental thing. The trouble is, imagine that I even explain something. Imagine that I say, I can explain this number by giving you a right-handed neutrino whose mass is 10 to the 8 GeV with these couplings, but you will never produce it. Will it make you happy? To me, again, it's semantics, unless I can imagine a physical way of checking it in reasonably near future. I'm not happy with an explanation. I don't want a mathematical, I don't want a formal explanation. I want a physical explanation that I can hope to see a trace of in the experiment. Mehmet?
Following this approach, we didn't include the Weinberg operator term, right?
No, we cannot include the Weinberg operator term. This is a physical theory. Now I'm writing the new standard model. I'm writing the non-minimal standard model. I got the Weinberg operator. Weinberg operator cannot be included. Weinberg operator must come from new physics. You cannot include it. You cannot include the Fermi theory. No, that would completely destroy the normalizability of the standard model. No, we say that the Fermi theory comes from the exchange. Well, now that you ask, we'll talk about it maybe more on Friday, but what really is happening, obviously, is this, that I have a left-handed neutrino entering, then through the Dirac mass term, it becomes a right-handed neutrino, which I call N. This becomes a right-handed neutrino, and then this guy gets a Majorana mass. So notice, this is a symbolically, this is a diagram, okay? This is phi 0 here. This is how we get the interaction. Remember how I got the Fermi interaction? I got it by exchanging the W. Here I will exchange the right-handed neutrino. The way it would look, and we'll come back on Friday, there will be a propagator which is 1 over k slash minus mn. Even the sign will come out correctly if you think about it. And when k is small, I will reproduce the operator. But truly speaking, there is always mn propagating. It's just when momentum is very small, and this is for us interesting when I speak of the mass and I go to the zero momentum, then I approximate this with 1 over mn. So Weinberg operator is the seesaw is a simplest modification of the standard model that produces Weinberg. And this has become the mechanism, okay? It's sort of, this is why it's being taught, even Alexei told about it, it's becoming the common language, right or wrong. I don't want to defend it to understand the origin of neutrino mass.
Oscillations are somehow related to this?
Well, once you get neutrino mass, you see what happens. If neutrino gets a mass, it will oscillate. Now the thing is that I wonder whether you did Alexei talk about it? He derived the oscillation, you told me. I would imagine that he would have mentioned that oscillations are insensitive to the nature of neutrino mass. In other words, Dirac-Majorana does not matter. Because what is happening in oscillations? You remember what is happening in oscillations? What really happens? That you produce electron neutrino somewhere in the sun, say, and then by traveling, actually this happens even in the sun, so sun is more complicated, you produce nu mu, say, in the pion decay, in the atmosphere, and then it oscillates because what happens is that the mass difference is so tiny that you cannot even sensibly speak of a physical state. Remember, nu mu was cosine theta nu1 plus sine theta nu2. And therefore, because of these states evolving differently with time or distance, this can actually become nu tau. But you see, a particle is becoming another particle. It's not really a particle. Particles are nu1 and nu2, and they never oscillate. It's not that someone oscillates. I don't oscillate ever into Mahmoud. But if the mass difference was so small that we couldn't distinguish us and we were produced coherently, then, you know, that strange sum could change into something else. This was not real oscillations. However, the point is that in order to see a Majorana nature of a particle, you have to create a process where the particle becomes antiparticle. You have to use that Majorana nature. Here, nu mu is becoming nu tau. Not surprising that neutrino oscillations are insensible to the nature of neutrino mass. And you must remember in the derivation there was never an issue of what the mass was. You just wrote the expansion, there was a little complication because they were 8 packets, but it was all boiling here that when you say that, say, nu1 in time is e to the plus or minus, it doesn't matter, e1t times nu1 produced. E1 square was p1 square plus m1 square. This was the definition. It was irrelevant. The mass was a kinematical mass. The mass was the dispersion relation of Einstein. It had nothing to do with the nature of neutrinos. In other words, if I want to see my Majorana nature neutrino oscillation, I would have to oscillate neutrinos into antineutrinos. That we can imagine maybe to somehow study. That's an interesting challenge related to a question. What would be the way to really see Majorana nature except for neutrinos double beta decay? Can we think of other processes like? I'll be talking about that. Or for example, could colliders, could LHC tell us something about it? But that we'll touch on Friday, maybe on Monday some more. We stop here. We turn the machine.